Hi, in this video we're going to solve an example to show how the synchronous motor can be used as a synchronous condenser to improve the power factor of the system. When this happens, you have here an equivalent circuit for synchronous motor, and usually if you use the synchronous motor as a synchronous condenser, they don't attach any load to the shaft of the rotor, and the current IA, if it's perpendicular, that's what we wish to be leading power factor. So if you have, that's the terminal voltage, and let's say that we want this current IA to be leading by 90 degrees, it means there is no power delivered to the stator armature line. That power here is equal to 0. It's ideal case, of course. So how you can find EF? EF, the field or the excitation voltage should be equal VA minus J XSIA. The RA is neglected here. We assume it equal to 0, the armature resistance. So you do to using the phasor diagram here. So you get EF, you subtract VA minus GXIA. How you do that? That's IA, and let me just sketch something here. If you have IA in this direction in general, the perpendicular to this phasor, that will be JIA leading, and that's minus JIA lagging. So according to this diagram, you can say that's IA upward. So the J will be in minus J will be in this direction. So you complete the phasor diagram by saying VA minus. So you finish at VA and then you make it the same parallel to this one. This is minus JIA, and then you multiply it by XS. So this vector from here to here is equivalent to minus JIA XS, and you reach the point here. So if you connect from the origin O up to the point here, that will be equivalent to EF. So what you obtain from here? So to have leading armature current, to have leading armature current IA by 90 degree also, not to consume any power. So what you will do, you do the excitation voltage magnitude bigger than the armature voltage. Not only that, and delta, as you see, is equal 0. It means EF in phase with VA. In this case, you get the current and the armature leading the voltage, so that will behave like a capacitor. So in this case, you can use it as a condenser to improve the power factor. All right, so that's what we got. Excitation voltage, the magnitude should be bigger than the armature voltage and in phase with the armature voltage. In this case, the armature current drawn from the system leading, and that will improve the power factor. Let's just take a numerical example here. Well, in this example, a manufacturing plant use 100 kilovolt and 0.6 power volt lag. So if you sketch that, you will say, okay, that's the system here, and there is a load here, and this load taking 100 kVA and 0.6 power factor and lag. When you look at this, you can make like a phasor diagram or the power triangle. So that's the Q, and that's the active power. That's a bit of power. So you got 100 kVA, and you got 0.6 power factor lagging. What does it mean? You can get, of course, phi. Phi will be equal cosine minus 1.6. You will get 53.13 degree. So that would be the angle 53.13. So you can calculate the power here. How we calculate the power of the load? That's the load that you have here, and that's the reactive power of the load. So the active power of the load will be equal 100 kVA times cosine the angle, cosine phi, that we have it here, which is equal to 0.6. So you got 60 kilowatt. So that's here the power, 60 kilowatt. And to find the reactive power of the load, you will have 100 times sine phi, which is 53.13, and you will get Q is equal 80 kVAR. That's 80 kVAR. So that's the information of the load that we have, and it's hooked here to the system. Of course, that's three-phase system. You can make it like that to make it like three-phase system. Well, let's just continue here reading the. A synchronous motor has a synchronous reactance of 4 ohm per phase and a negligible armature winding resistance, R is equal 0, is added to the system. So you want to add a synchronous motor system here, obviously, because you want to improve this poor power factor. So they connect a synchronous motor, three-phase, and the reactance is equal 4 ohm per phase. That's XS. That's the information we got. And that's, of course, the voltage will be the same. You have 440 volts, it will be applied to the load, applied to the synchronous motor, the same thing. So let's just write that the system is 440 volts, line to line, of course. So you have the synchronous motor, that's the only information. But they want to improve this poor power factor from 0.6 to 0.9. So the question is, what is the excitation voltage of the synchronous motor that will help us to improve the power factor to 0.9 lag? Okay. The first part in the problem, you do not involve the machine as a machine. No, just involve it as any element that will improve the power factor. What does it mean? It means if this is the load before connecting the synchronous motor and you want to improve it to 0.9, it means that you are going to decrease QL. So let's just make it bigger here. So it means that you look for 0.9, what's the angle here? So the new angle, let's call it phi 2, the new one, that will be equal cosine minus 1.9. Remember, the old angle is 53.13. So 0.9 cosine minus 1, this power factor will give us this angle, 25.84 degree. So the angle will be less, so you can say here, that's the new angle. The dark one here, that's will be 25. That's the total angle. So that will be the whole thing. So how will be decreased to this amount? So this part has to be supplied by the synchronous motor. Why? Because synchronous motor is leading and the load is lagging, so that will be the opposite, will be in this direction. So that would be this blue part just I did, that's the Q of the synchronous motor. That's Q of synchronous motor. All right. We can make now calculation. That's the new one, the total after the improvement. Can you get it? Yes. Because remember, the power stayed the same. PL is equal 60 kilowatt, the same. So the resultant power triangle, after improving the power factor, I'll just make it separate here. You get the same power, 60 kilowatt. And that's the new one, call it QT total. And you got the new power factor and the new angle was 25.84. And then we can calculate the total reactive power after the improvement. How you do it? Using trig, you see, the ratio between QT and the power, which is 60 kilowatt, it's equal tangent of the angle, tan of 25.84. From this equation, you can get the new value of QT. Doing that, so you will find is equal to 29 kVAR. So that's the new value of the reactive power to have better power factor. And the old one, before connecting the synchronous motor, was 80. So where is the difference come from? Come from the synchronous motor. So now we can say the reactive power of the synchronous motor that supplied by the synchronous motor is equal to difference between both 80 minus 29. It will give 51 kVAR. So this value will be supplied by the synchronous motor or the synchronous condenser. Well, how you calculate the corresponding excitation voltage for the synchronous motor? Take it step by step. First, let me remind you about what we said. The synchronous motor acts as a synchronous condenser when the current is leading the terminal voltage by 90 degrees. So to calculate the reactive power in this case, you will say the reactive power of the motor is equal 3 armature voltage magnitude times armature current magnitude times sine phi. In our case, phi is equal 90 degrees leading, right? So it will be 3 VA, IA, and sine phi will equal 1 because phi is equal 90 and sine 90 is equal 1. So that should give 51 kVAR. The armature voltage is given, it's because the synchronous motor connected to the system by 440 volt. So the armature voltage will be the phase value, and you can get it by dividing 440 by square root of 3. That will give you the phase value. If you don't want to calculate the phase value, you might use different equation. You can say it's equal to square root of 3 and the line voltage and the armature current. You can do the same thing. Of course, sine phi is equal 1. You can do that. Okay, let me do that. That's a different way. Square root of 3 times V line, which is 440, times IA. So now we can get the magnitude of the armature current. So IA will be equal QM, which is equal 51 kVAR divided by square root of 3 times 440. It will give you the armature current. And if the synchronous motor is equal, almost you can say 67 amp. So that's the armature current. Remember, we need to find the excitation voltage. All right, but this is the magnitude. You tell me now, I wanna express it as a phasor. Well, it's 67, and what's the angle? It's leading the armature voltage by 90 degrees. That's it. It's easy. That's the armature. All right. We still need to find EAF. Well, that's the circuit of the equivalent circuit of the synchronous. Now we got to use the phase value, which is 440 divided by 3 angle 0, and the armature current we just got 67. That's IA phasor, 67 angle 90 degree, and the reactance of the synchronous is equal 4 ohm. And now we can get the field or excitation voltage that will help us to improve the power factor in this case, because we got IA. And remember, IA, we got IA from QM, from the reactive part. So now EF is equal to VA minus GXS IA. That will be equal 440 divided by square root 3 angle 0 minus J4 times the current 67 angle 90, and you get EF. And if everything is fine, you get 522 and angle 0. No wonder angle 0, because we expected that is in phase. The excitation voltage should be in phase with VT. So to improve the power factor to 0.9, you got to have excitation voltage EF magnitude is equal 522. Of course, this is per phase. You got to say this is voltage per phase. So to find the line to line, you just multiply it by square root of 3. It will give you the value that it will help you to improve the power factor. That's it. Thank you.